higher energy, so it can more easily diffuse. It does not have to go as far to get over a saddle point. So the diffusion activation energy is reduced. You diffuse at lower temperatures. And in fact, calculations by Richards, preliminary calculations, I should say, suggest that the separation in temperature between this stage and this is semi-quantitatively consistent with what we see. So all of these indications are basically going to make the point that we believe we do have a palladium matrix in which all of the octahedral sites are essentially filled, and we have superstoichiometry, about a 30% excess in the lattice. And then the question is, does that have any influence on cold fusion? And I'll say immediately that we, in fact, were not able to detect any evidence of cold fusion occurring in our materials after the ion beam was turned off. The upper portion of this view graph gives some of the relevant conditions. This is 397 palladium. We investigated two conditions: cold rolled material, and then material which was annealed at 1,000 degrees under a high vacuum. The deuterium to palladium atom ratio, as I indicated, 1.3. The amount retained in the material is about 10 to the 18 per square centimeter. 2 minutes. Thank you. And this is the detector solid angle. There are three experiments represented here. In one case, we implanted the saturation at 40 Kelvin, and then we remained at that temperature with the charged particle detector running, no beam on the sample. During this time, in the detection system, we got one count. Our detection system does have some background, and which is indicated in parenthesis there. And since that is an important issue, I would just like to return to it, to the details of the detection process. We focused specifically on the protons, and for the detection window, this is again when we're hitting the sample with deuterons and producing copious protons. This, in fact, would occur in only a couple of minutes with the beam on. But anyway, we would define a window here for the detection of 3 MeV particles, and then a broader segment on either side to define the background. This then is the background level that scaled down to the width of the window here. So, I mean, obviously, no evidence of cold fusion under these circumstances. In another case, with the thought that greater thermal agitation at 81 Kelvin might have some effect, we did a similar experiment and a similarly negative result. And yet another experiment, we implanted the saturation at 81 Kelvin, and you recall that by the way, the loss of superstoichiometry occurs at about 120 Kelvin. So here we still achieve a high the superstoichiometric condition. Just to be thorough, we did in fact warm from 81 to 230 Kelvin, and again a negative result. We have, in this last column, normalized, again, we see no evidence of cold fusion. In describing estimated bounds on the reaction rate, we have normalized to the number of deuterons in the material, and we then come up with bounds, upper bounds on the reaction rate in this range. Now, obviously, here we are talking about bounds that are substantially above the very low levels that have been reported by Jones and others. And in fact, with these implantation experiments where the number of particles we're monitoring is comparatively small, we're not going to extend our bounds down to 10 to the minus 24. But again, the principal objective in doing these implantation experiments is to see if there's something special about superstoichiometry. That was the specific objective. Good. And so and in fact, under those circumstances, this, by the way, of course, is very small compared to what would be necessary to get the Pons-Fleischmann level of reaction. But we see no evidence of cold fusion. In conclusion, I will simply mention that we have done analogous experiments in titanium and zirconium following essentially the same procedures, and we have not detected statistically significant charged particle yields there either. Thank you.
Thank you, Dr. Myers. The lecture is open for discussion. There's immediately a very quick response.
Rod Sharp Associate, Santa Fe. Why is it so difficult to get one-to-one stoichiometry? I mean, the binding energy looks like it's positive in these octahedral sites. Why don't we see a plateau at one-to-one?
You're saying why is it difficult to get to one or above?
No, to why isn't there a stable plateau at one-to-one stoichiometry? Why don't we get there easily?
Yeah. I think that it relates to entropy comes into this, and I believe it is not only the energy of the sites but also the statistical entropy. The entropy goes down when you basically fill all the sites. So I think the chemical potential, which is a combination of both energy and entropy, goes up as you approach one. And of course, there is a big leap when you go beyond, as is clear to you, I think, several tenths of an EV.
Richard Petrasso from MIT. I have two questions. One, Ed Cecil yesterday showed results quite similar in nature in types of experiment. I guess he was loading in deuterium maybe at 95 kilovolts instead of your 10. One, he reported observation of particles at about 5 MeV. One, did you search up high enough in your MCA that you could have seen such effects? I think, although I don't know if Ed Cecil's here or not, but I think it was probably done at room temperature, his experiment. And maybe you could comment also on his signal, which I think was at about 5 sigma and was, I think, sort of a hint maybe would be.
Yeah. I think I will be interested to see how those experiments to develop. You correctly enumerated the differences. We implanted at low temperatures to achieve superstoichiometry, and in fact he did it at room temperature. I'm not altogether sure what concentration level he reached at room temperature, but presumably it would not be superstoichiometric. We in fact did not pass current through our specimens, and I mean, as I understand it, that was a key factor there. You ask about 5 MeV, we would have seen particles there. I mean, I would estimate that we would extend out to about 10 MeV particles. I would say that I showed only a portion of the spectrum, but in fact we went out, much further than this in the detection system. So if we were getting singly charged nucleons at 5 MeV, we would have seen them. But again, we are talking about rather different experimental conditions, and our focus was specifically on superstoichiometry, which may or may not bear on cold fusion. Certainly, we did not get any statistically significant results.
Well, I'd like to make one quick comment, and that is that everyone's been talking about the importance of 0.7 stoichiometry, and Cecil, I believe from the inferences, is he must have been not above 0.7.
Well, I would not make statements about that.
It appears is all I'm saying. Thank you.
Yeah, that's right.
William Lindlar, Thermalistics. Did you by any chance have the opportunity to look for excess heat production after you turned off the beam?
No, we didn't, and we did not do such an experiment, and naively I would think that given the fact that we're dealing with, although a high concentration, a small actual volume of the deuteride, that our chances of seeing it would be rather small, because again we're working with 10 to the 18 atoms altogether. So.
Goldstein, Westinghouse R&D. In the relationship between what you were doing and the other experiments, the electrolysis experiments, what would you expect the impact of the radiation damage that you produce? Would that tend to disrupt, you might say, any DD fusion that people are seeing in their electrolysis? I mean, to make the situations rather dissimilar.
That's a very good point, and this is something that, in fact, in collaboration with the previous speaker, Bessenbacher, we've examined at some length. And I think, yes, we certainly do create radiation damage with this implantation. And in fact, one can rather strongly trap up to perhaps several atomic % of hydrogen in these defects. So that would certainly be, I think, an effect going on in this system. However, compared to a 30% excess, I think that's a small effect. And in fact, I didn't elaborate here, but we've done other experiments where we go up and actually follow the release curves down to much lower levels, and you see defect trapping very, very clearly. But again, the amount of hydrogen involved is rather small compared to the levels we're speaking of here.
Johnston, ISCMNS Energy, Quebec, Canada. When you, in a tokamak, have deuterium banging onto the edges of things, and you stuff a lot of deuterium in it, usually the surface looks absolutely terrible. Did you look at your surfaces before and after?
Yes, we did, and these implantations were done under fairly high vacuum conditions, about 10 to the -7 torr, and you do get sputtering, but the surfaces still look smooth. Now, if you go to very high doses, you ultimately will get some blistering. And I think as compared to the interior of a tokamak, we did not get those highly disrupted conditions. The saturation, if you go to very high doses beyond 1.3 and keep putting it in, it does appear that ultimately you'll get some blistering, and we've seen that as well, and I didn't address that. But
try to stay to the point. There are many questions which I can see. Please try to be very brief. We are running late.
James Aird, Naval Research. To resolve the point between Cecil's work and your work, we did the same experiment at low temperature and passed a current through it. So we sort of covered two bases there.
Oh, good. What was the finding?
We couldn't find any counts.
Ah, okay. I'm intrigued by that. May I ask if you counted for an extended period as he did, or?
We went for. So we did the same, much the same experiment at low temperature, but we passed a current through using the ion beam to generate the current because we're in an insulator. We counted for about 3 hours and found no counts. That's a lower, that's not as sensitive as Cecil's work. He counted for a much longer time. He counted for 90 hours, and he had a higher solid angle. But we did pass a current through it and had the same low temperature that you had and found no counts.
Please, all those who have urgent questions, raise your hand once more. They were in the back. These two gentlemen. The last two questions. One and one there.
Ed Storms, Los Alamos. I have two questions. Is it possible that your stoichiometry could have a 20% error such that your 0.8 was really 1.0 and the region where you had no change in stoichiometry was the two-phase region between 1.0 and the next higher phase, whatever composition that is? That's the first question. And the second one is that it's very possible that at low temperatures the deuterium atoms go into the lowest energy sites, which would be the octahedral first and then the tetragonal.
As long as the octahedral guys are available, once you get to one, then it has something else that has to happen.
It has to go someplace else, right?
Yeah.
But is it not also possible that since there would be a very high energy associated with dual occupancy of the octahedral site, where most likely fusion would take place, that high temperature coefficient associated with that high energy would require you to go to higher temperatures before you get a rather infrequent dual occupancy, and therefore fusion would only take place at the high stoichiometries at high temperatures, or at least much higher than yours.
Okay, let me take those in order. How well do we know those concentrations? I might add that we are, at Sandia, we are well positioned to do accurate composition profiling, but on short notice it was not consistent with low temperature implantation. We didn't bring the two together. So the concentration measurements that we have here are less accurate, as you perhaps well know, than one would have with detailed high-energy nuclear reaction profiling. Nonetheless, I don't think it was 1. It might have, I would say that if we did not have the independent information, I would say 1.3 plus or minus 0.1 and 0.8 plus or minus 0.1. I don't think it was 1, at least not in the near surface region where we were sensing. To sort of give somewhat rambling answer to the other, yes, I think that first, the excess hydrogen we believe on theoretical grounds probably goes into the tetrahedral site as opposed to multiple occupancy of the octahedral site. And I think the other point you made was, by being at low temperatures and not having the thermal agitation, are you not losing a lot? We may very well be. I tend to agree with you, and we don't understand cold fusion, so we don't know what's important. We simply wanted to see that if you supersaturate, albeit at a low temperature, what happens. But I agree with you, if it happens, you would think that thermal agitation could be a very important element.
Thank you very much. Okay, we proceed to the next item. Thank you very much once more. Yeah, we are running very late, so the break will be very short. Please, all speakers, please be very brief. Dr. Biegeleisen on tritium enrichment and the electrolysis of D2O from the State University of New York.
I'd like to make a few remarks about the tritium content of heavy water as it's manufactured, and then a few remarks about what happens to the tritium content of heavy water when you electrolyze it. I'm not going to address the question of tritium content of heavy water, which has been used as a moderator in a nuclear reactor, or been reprocessed after that, or special preparations of heavy water which have been manufactured for, say, bubble chamber work to reduce the tritium level. What I'm going to address is the tritium level in heavy water as it is manufactured in a commercial plant. Well, the concentration of deuterium from protium in a commercial plant also enriches the tritium, and it enriches the tritium more than it enriches the deuterium because of the larger mass difference. The final concentration of the tritium in the heavy water depends primarily on 3 factors. One is the tritium content of the feed water to the plant. 2 is the method of manufacture. And 3 is the age of the heavy water after it has been manufactured. Most natural abundance of waters, surface waters, which have not been contaminated by bomb tests and other things like that, generally have a tritium to protium ratio of approximately 1 tritium unit, which is 10 to the minus 18th tritium atoms per proton. And detailed surveys have been made of surface waters. One particular one reported by Libby in 1960 shows variations of different surface waters, and in particular also tritium units, tritium levels as high as 100 tritium units in areas close to hydrogen bomb tests. So what I'm going to do is to make some calculations on the basis of the feed per tritium unit of feed. Now, most of the heavy water manufactured now in the Western world is manufactured by the so-called GS process, which is a process which exchanges hydrogen sulfide gas with water feed. And this is a schematic diagram of the primary enrichment stage in one of these plants. Plants of this type were built in the United States originally in the early 50s at Dana Wabash River Ordnance Works in Indiana, then the subsequent plant at the Savannah River, and now the largest capacity has been built in Canada in order to feed their CANDU reactors. Basically what you do is you feed heavy water from a river into an exchange tower, which is at 30 degrees centigrade, and this consists of many plates. The current Canadian plants have towers 200 feet tall, approximately 10 feet in diameter. There's hydrogen sulfide coming up counter-currently, and let's concentrate our attention at this point here at the feed point. Because of quantum mechanics, deuterium is transferred from hydrogen sulfide to the water, and deuterium and tritium, also the heavy isotope, always favors the water. Now, this hydrogen sulfide is sent around in a loop, and here it contacts hot water, 130 degrees centigrade at high pressure, and here this reaction is not as favorable because it's a quantum mechanical effect, and it follows essentially the Boltzmann principle, and so some of this deuterium here in the hydrogen sulfide is then back transferred to the water, but the water here now, this is at a higher temperature, the equilibrium constant is lower, so the water is depleted, and water which started in at 145 ppm deuterium exits at 120 ppm, roughly 17% of the deuterium is extracted. So in a series of columns of this type, you can extract deuterium. What you'd like to do is extract them at a high level, and that's the purpose of having these two columns, which establishes a concentration gradient. Here, the deuterium concentration builds up here and then goes down here, and you bleed off 15% heavy water. This goes now to a higher stage where the deuterium is enriched further, and then the protium from the higher stage is fed back here. I don't show that. In any case, the fraction of the deuterium extracted simply depends on the ratio of the enrichment factor or the equilibrium constant of this reaction at the bottom of the column here to that at the top of the column. Now, it's easy for us to calculate this ratio also for tritium, and so we know what fraction of the feed of the tritium in the water would be extracted in this heavy water plant. So in a GS plant which extracts 17% of the deuterium, you would extract something like 24 or 25% of the tritium in the feed, and this eventually ends up giving you heavy water with a tritium content of approximately 6.5 times 10 to the 8th tritium atoms per cc of heavy water per TU unit of feed. Now, processes which are more efficient for the extraction of deuterium will have a lower tritium content because of the fact that you don't need as much tritium, as much water feed to produce a cc of heavy water. All right, now, we know from the work of Washburn and Urey that in the electrolysis of water, the heavy isotope concentrates in the water phase. The amount of enrichment depends on the kind of electrode you have and the current density. In the 50s, when people started measuring natural abundance of tritium, Libby came up with the idea that to improve the determinations at low-level counting, it would be advantageous to pre-enrich the sample that you want to analyze for tritium. And to monitor the amount of enrichment, what you do is just monitor the deuterium enrichment in the same sample, and even though the separation is variable, depends on from one experiment to another, this depends on the current density, nature of the electrode, and so forth. His idea was the relative enrichment would be relatively constant. Well, I worked out the theory of this, and about the same time I worked on the theory, Ostlund, who had been making routine studies of natural tritium levels, made a thorough study of the relative tritium enrichment to the deuterium enrichment in the electrolysis of water. And here are a series of his experiments, and this is the logarithm of the deuterium enrichment factor, which is the relative rate of electrolysis of H2O to that of HDO, and this is the relative tritium enrichment, and you see there are large variation in the both the tritium and the deuterium enrichment factor, and this is the theory of the relative tritium to deuterium enrichment in water, as you calculate it from first principles, and you see we understand this very well, and so you can easily calculate the tritium enrichment if you know the deuterium enrichment. So I've made some calculations of the tritium enrichment and the electrolysis of heavy water for a range of deuterium enrichments given by this range here. And of course, the final overall enrichment depends on how much heavy water you electrolyze. If you electrolyze a tenth of a percent of the heavy water, clearly you don't change the tritium level of the heavy water. If you electrolyze a very large amount, then you concentrate the tritium in the heavy water. And this final slide shows the separation, which is the specific activity, the tritium to deuterium level in the final heavy water compared to the tritium to deuterium ratio in the starting heavy water. And that's calculated by just the stoichiometry of the reaction, the Rayleigh distillation formula. The logarithm of the separation is the ratio of the tritium to deuterium separation factor minus 1 times the logarithm times 1 minus f, and 1 minus f is simply the volume of the deuterium heavy water at time t divided by the initial volume of heavy water. Of course, this is for the case where you just start with a given batch of heavy water and you electrolyze it down. If you then start adding subsequent aliquots of heavy water, then you have to go through an iterative process. So let's say if you electrolyze 60% of the heavy water, you might enrich the tritium by a factor of 1.4 to 1.65. If you electrolyze 95% of the heavy water, the enrichment is going to be a factor of between 3 and 5. So these are the kinds of enrichment you're going to get in the electrolysis of heavy water. And this range of enrichment explains quite a number of the reported tritium enrichment experiments reported. It does not cannot by any means explain the tritium levels reported by Kevin Wolf. Thank you.
Thank you very much. Yes, there's a question right here.
Yes, Jean Paquette from Atomic Energy of Canada. I think it's important to point out that this electrolytic separation does not occur if you recombine all the gases.
I didn't get you.
If you recombine all the gases with a recombiner, you don't have electrolytic separation.
Yes.
It occurs only with open systems.
Oh, yes, correct. Yes, of course. Oh, I want to thank you for mentioning that fact that you are from Canada. The current level of tritium in the heavy water plants operating in Canada now, it corresponds to roughly 180 dpm per cc of heavy water, which then would correspond to something like 3 TU of feed.
And there's one very urgent question.
Dennis Corrigan, General Motors Research Labs. I just want to comment that we measured the separation factor for deuterium, tritium at palladium intense molar lithium OD and found it to be about 2. And if you used 180 dpm per mil, this would explain the 100 dpm per mil increase that Fleshman and Pons reported in the 16 days that you can calculate that they did their electrolysis from their paper. However, in Dallas, they did report that the tritium concentration in their heavy water was only 18 dpm per mil. And if that's true, then you cannot explain the 100 dpm per mil on the basis of separation effects.
Well, I would say that one has to look with suspicion on an electrolysis experiment in which an appreciable amount of the heavy water is electrolyzed and you don't find any tritium enrichment. I mean, after all, there's 55 years of experience with this, and there are large commercial plants that operate on enriching producing heavy water by electrolysis of deuterium, using not palladium electrodes, using iron and nickel electrodes. The palladium electrodes give lower separation factor, and they would be in this range here.
Right.
Cornog, unaffiliated. We electrolyzed heavy water which contained tritium, which had been recovered from circulating the cyclotron just 50 years ago today. And in electrolyzing that water, we electrolyzed from about 2.7 cc's down to 1 cc, and we did detect detectable enrichment of the tritium at the beginning and the end of the electrolysis. The tritium was quite detectably enriched.
Thank you. There's one last question over there on the other side.
Thank you. Roland Jalbert, Los Alamos. I have a comment to make which I think is fairly important for a lot of people who work with D2O and perhaps work with deuterium gas also. This comment, this seems to fit this particular talk. It's not a question, but it is directed towards a comment made last night by Nate Hoffman about the concentration of tritium in deuterium gas and how that differs from the concentration you normally find in heavy water. At Los Alamos, we've measured in the past concentrations of tritium in deuterium gas ranging from 10 or so microcuries per cubic meter up to 100 or more microcuries per cubic meter. If you take an average of about 50 microcuries per cubic meter, that translates into a T to D ratio of about 2 times 10 to the minus 11. Now, if you look at the heavy water that people have been using for electrolysis, that ranges from about 100 D per M per milliliter to, at Los Alamos, we've measured up to 300 times that. The 300 times that value corresponds pretty much to the ratio of T to D in the ordinary deuterium bottle gas that you would get out of stock, and you're not paying too much for it. If you calculate the T to D ratio for the 100 D per M per milliliter heavy water, as was used at Texas A&M, you find that that ratio is about 2 times 10 to the minus 14. So there's a difference in concentration of T to D in the gas versus the heavy water in this particular example of 1,000. So for those people who are doing electrolysis with, say, 100 D per M per milliliter of heavy water, and you happen to have some deuterium gas around, you think you can use that gas for purging the water or doing other things with it, be careful, because the concentration of tritium in the gas could be very much higher, as Nate Hoffman indicated last night. And that difference is substantial, or could be substantial, namely 1,000. It could affect the results of the experiment.
What's the history of that deuterium gas, which has 1,000 times the specific activity of tritium compared to commercial heavy water?
Well, the history is unknown to me. It's stuff you normally get and you don't pay too much for. It's the stuff that's in a bottle that's labeled radioactive, and yet it's deuterium gas. This is a DOT regulation that was put in force about the time that we were making these measurements about 15 years ago. And up to that time, the deuterium gas bottles was not labeled, or were not labeled, and they started labeling them radioactive at that time because of the DOT regulations. But I'm sure you can get deuterium gas that has less tritium than the stock stuff for which you don't pay excessive amounts. Okay.
Well, actually, if you get some old cylinders of hydrogen, and let's say cylinders of hydrogen that were prepared before 1952 or something like that, and if the hydrogen is made by electrolytic hydrogen, then it's well known that hydrogen gas is well depleted in deuterium because of the electrolytic process, and also well depleted in tritium. So a deuterium gas sample that has 10 to the third times the specific activity of a commercial, of a sample of heavy water from a commercial heavy water plant has been contaminated with tritium from some way or another, either from reprocessed heavy water from a nuclear reactor or some exposure from some actual tritium source. Because any kind of chemical reaction or equilibration of deuterium gas with heavy water will automatically concentrate the tritium in the heavy water, not in the deuterium gas. To do it the other way means you've got to beat the second law of thermodynamics.
I think we have really to stop the discussion here and thank our speaker. Thank you very much. Next we have a lecture on nuclear fusion from crank-generated particle acceleration by Dr. Meyer with collaboration with King and Reitz from Ford Motor Research Laboratory.
That's right. Well, first of all, I'd like to thank the committee for allowing us to come here and present these ideas. When we first started thinking about such things, it wasn't clear to us that anyone would be thinking in terms of strange processes for cold fusion to take place. And so we decided to take a look at what might be called rather conventional ones. So we're going to talk about nuclear fusion from crack-generated particle acceleration. And we're finding now at this meeting that a lot of people are talking about microcracks and fissures and fractures and lots of things, which, by the way, I know very little about, but I think I know a little bit about accelerating deuterons, so we'll talk about that. I'd like to thank my associates, my colleagues, John King at the University of Michigan and John Reitz, who was formerly with Ford Motor Company Research and who is now retired. We want to consider what we think is a rather familiar mechanism in a rather unfamiliar place, inside a metal. And that is electrostatic acceleration of deuterons produced by fields created by charge imbalance across cracks. And what happens, we think, or what we're proposing, is that hydrogen loading produces lattice stress, lattice cracking, charge imbalance, the gap opens up, and this capacitor-like nature raises the voltage, okay, until you get to a voltage at which the deuterons are accelerated to kilovolt energies. And those, as you know, are standard energies to make ordinary nuclear fusion events occur. We found out on Friday that Firth et al. Had proposed a similar mechanism at the Baltimore APS meeting. So a number of people, I suspect, are thinking along the same lines. Okay, the voltage across a crack, and we're thinking about the crack in a very simple way. We're thinking about it as a capacitor. the voltage across the crack as a capacitor, it's easy to show that that voltage is equal to 10 to the 9 eta D. This is an MKS, by the way, unless it's otherwise indicated. And where eta is the number of imbalanced charges per square lattice, or lattice square. In palladium, there's like a 4 angstrom linear dimension, so it's 16 square angstroms. And so if you plug in some numbers, let me choose 1 electron per 10 square lattice areas, okay? And let me then ask the question, given 2 different dimensions of gap separation, 1/10 of a micron and a micron, what voltages then would occur if the gap opened to those dimensions? And the answer is, why is this in the road here? Oh. Oh, there. Gravity. Okay, so those correspond to gap voltages of 1 kilovolt in the 10th micron case and 10 kilovolts in the 1 micron case. And remember, those are just 2 numbers I'm going to plug in because I think that gap separations might be in that region between 1/10 and 1 micron. Okay, now, if those potentials develop, and a stray deuteron in that gap falls through that potential, okay, it gains that energy in the classical fashion, right? Same way any beam is accelerated. And the reaction rates then, when that deuteron is accelerated and runs into a deuteron in the lattice, makes nuclear reactions rather efficiently if that, in particular, if the energy is higher than a few kilovolts. This is just the nuclear reaction rate using a density of deuterons, which corresponds roughly to 1-to-1 deuteron loading in palladium. And I show this only to show that at the 1 kilovolt level, you need quite a few deuterons to get like a neutron per second. On the other hand, if the gap separates to a micron and you get 10 kilovolts, you need roughly 1 to get neutrons per second. I consider that important because that's a small number. There's not a lot of particles involved, yet to make that number of neutrons, which are the neutron levels, I believe, that are being seen. It may actually be a little bit bigger. Okay, now, this is easy to propose, but then it's easy to shoot down. You say, well, why doesn't that crack, that little capacitor, discharge? And the answer is it should. Well, what's the discharge time? Well, it's the RC time constant of that capacitor discharging around the crack and the resistance around the crack. Now, the question is, how long do you have to have the charge maintained to get the voltage up to that level before the thing shorts out? Well, we estimate, and by the way, this is wrong in our abstract, we estimate that time to be the gap dimension divided roughly by the speed of sound, which should be the opening speed of the crack. So what are those times? So, well, those times, again, the RC, then, of that circuit has got to be greater than the gap dimension divided by the speed of sound. So for our 2 cases that I want to focus on, that's about 50 picoseconds for the 1 kilovolt gap and 500 picoseconds for the 10 kilovolt gap. Now, the first point is those times are not very long. And you know that if this material was a dielectric, you would have forever. I mean, more or less, right? If you rip that off quickly, what happens? Well, you build up charge on this stuff. By the way, that's the same process, right? It's a mechanical separation of charge, which then leads to high voltage. It's like capacitor, and you move it apart, right? So what happens? Well, you develop that voltage, you accelerate particles. All right, so let's take a look now at this simple model of a capacitor. And I want to deal with this because it is simple. It's a capacitor that's shorted at one end. And I want to do that RC time constant. I want to calculate it. All right, so we consider the capacitor to be shorted at one end. The resistivity around the loop is the resistance times the path length. You know, the resistance is rho L on A. The capacitance is epsilon naught A on L, or D, rather. So you can do that calculation. If you do it, you find out, first of all, an interesting thing, that time constant doesn't depend upon the width. It depends strongly on the resistivity of the conduction path, the conduction path depth, which is little d in my nomenclature, and the resistivity. Okay, now, so basically that's the time constant which you have to maintain to get the voltage up to where you want it, okay, to make this happen. Okay, so what do I take for the resistivity? Well, I've chosen conservatively to use the bulk resistivity of hydrogen-loaded or deuterium-loaded palladium. So if I use that resistivity, the only number I don't know in this simple model is the length of the crack to give me an RC time constant long enough to support the charge. So I can say, how long does the crack have to be to give me that time? Okay. So again, as I said here, I'll use a conduction path distance of like 100 angstroms. And let me say, we can play with these numbers, and you can move them around, but the bottom line is they're roughly in similar domains. But the point is, then, to get the RC time constant long enough, we need, in the 1 kilovolt or 0.1 micron gap, we need to get beyond this region, which, to get the time constant long enough, which is roughly a few hundred microns of gap length to give me time enough to get to a kilovolt across that 10th micron 1 kilovolt gap. For 10 keV, which in some sense is better because you need many fewer of them to get the neutron rates, you don't have to get much larger crack. You only have to get out to about 1,000 microns. Now, so again, in the two cases, it's saying that with this resistivity value, cracks of the order of 500 to 1,000 microns give me time to get the voltage up when the gap separates. 2 minutes? Oh my gosh. Okay. The question is, the resistance itself can be much higher. First of all, I showed you a perfect capacitor. Now I'm going to show you a little more irregular gap, or crack. The point is, many things can contribute to the resistivity as seen by electrons trying to short circuit this capacitor. One, it's just the circuitous route that an electron has to take to discharge the crack. The thin conduction layer of 100 angstroms could be smaller. I mean, it's not clear what it is. There could be other smaller cracks around this main crack, which would certainly add to the resistance of any electron trying to short the gap. There could be phase transitions near the crack surface, around the crack tip. Cracking is rather a mechanical process. I suspect there's a lot of phonon noise. Electrons scatter off phonons, so it could be increased that way. First of all, and even in bulk metals, the resistivity near the surface is higher, considerably higher, than it is in the bulk. Again, the reason is the mechanical or the quantum mechanical edge effects. Electrons tend to see the edge. If, take a look at Cattell, you'll find that described. It can be 50 times as high as the bulk. Okay, the question is, are cracks observed? And the answer is yes, and a lot of people at this meeting are talking about them. Large cracks are observed not just since cold fusion started, but in hydrogen-loaded palladium. Here's a picture of one. You'll notice, first of all, that this crack, at least in the picture, doesn't extend to the dimensions that I suggested, but and it's a poor reproduction, but nonetheless, the gap spacing can be substantial, yielding substantial voltages like I've been discussing. Okay, well, let's suppose cracks are what's going on. The question is, how do you maximize cracks? Let's make as many neutrons as we can. Well, this reference, which some other people have already mentioned at this meeting, the Soviets, Klyuev and et al. Have measured neutrons from fracturing of LID. And when we found out about that, this was after we'd done the calculation, we were all excited. Oh, well, that's okay then. Except that was before we thought a whole lot about this question of resistivity. The point is, again, lithium deuteride is a dielectric. You charge it up, it stays there a while. By the way, they see roughly, with a gas gun and a projectile hitting lithium deuteride, roughly similar numbers, you know, as to what's seen in cold fusion. So maximizing cracks. And by the way, I want to mention that some people at Los Alamos, Bob Ryan and Tom Dickinson at Washington State, have made measurements now where they have seen energetic particles coming out of cracked material. By the way, that's not new. Mechanical energy delivered to lots of metal materials produce energetic particles. It's one of the ways it gets rid of that mechanical energy. Okay. The Soviets have done a lot of work on X-rays emitted from cracked materials. Okay, so then the time is just right. In conclusion, nuclear fusion reactions in deuterium-loaded metals may be the result of cracks generating localized charge imbalance and particle acceleration. This mechanism is rather conventional. It's not exotic. It's not exotic nuclear physics. It's not exotic plasma physics. It's not exotic anything. It's just a crack in a material. And I suspect if people who study such things in materials would come back and look at this, I'll bet they would find that to be the case. I want to say also that if this is the mechanism, it seems highly unlikely to us that it would scale to a useful energy source. Thank you.
I'm sure there will be many questions. We have considered that there will be no break if there are too many questions.
You mentioned the X-ray, Richard Petrasso from MIT, you mentioned the X-rays from the Russian experiment. Am I correct, one, in assuming that that's due to an electron acceleration?
Sure.
And secondly, it gets back to the Los Alamos experiment where they had the X-ray detector. My guess is that you'd probably accelerate many more electrons and generate many more X-rays. I guess, do you have any speculations, or maybe from you or from them, on why they didn't see any?
Well, first of all, the voltages are low. I mean, that's one thing. And in fact, I suspect that the statistics would be, well, no. The answer is I have speculations, but that's all they would be. I suspect that the energies of those X-rays would be low. I believe the statistics would be, in a similar way, need to be measured in the same way as we're having trouble measuring neutrons in these bursts. Namely, you'd have to time it pretty well. You'd have to use similar, counting statistics.
Fred, there might be a little plasma physics lurking in there. If you have a material that's stuffed full of deuterium, which is thinking of getting out, and you try to open it quickly, it's quite possible that the thing might be, if you like, a vacuum breaker or a circuit breaker in vacuum, that you could create its own little plasma between the bits and sort of short circuit a lot of the stuff you're talking about.
Well, yes, Tudor, that's true. The point there is, I think that is also a possibility, that you produce a plasma in the gap. In fact, if you figure out how much mechanical stored energy you may have making that crack and distribute that energy in any way in the gap or around the gap, you get very high energy density plasmas, which, by the way, is heating. Releasing mechanical energy in that lattice heats the lattice. Yeah.
Birnbaum, University of Illinois. I just want to point out a couple of things. One is that if you watch the fracture process during electrolytic charging, you'll find that during the charging, there is no cracking. The cracking, the stress at the surface is a compressive stress. You get plastic deformation in the interior. You don't get cracking until you stop charging and the hydrogen is removed. Now, if you believe that neutrons are coming out as a result of charging, you're finding the neutrons.
Well, I'm just saying that a crack will develop. And when the crack happens, I don't care if you have the voltage on or not, any more than I need a voltage applied when I take this thing and I go like this. What do I get over there? I get little sparks. If I deuterated this stuff and you guys put sensitive detectors there, I bet you make neutrons. Oh, I'm sorry.
Yeah, I want to congratulate you on a very original mechanism. I'd like to suggest another version of it, though, which could explain the adventitious character of the so-called cold fusion. Suppose you consider that the crack you're talking about is in fact the electrical double layer. The double layer between what stands just outside the electrode surface and the surface. And if you have a really smooth surface, an atomically smooth double layer, the field across it is about 10 to the 8 volts per centimeter. And when you calculate the acceleration of a deuteron across that, you get a few electron volts. No good. But yesterday, somebody came and showed me some pictures of my surfaces taken on an electron microscope. And part of them were covered with dendrites. Dendrites have tips which are about 100 angstroms in radius. And at those tips, you develop fields of about 10 to the 10, 10 to the 11 volts per centimeter. Now the acceleration of the deuteron.
Can I make a comment on that?
Yeah.
Yeah, that's true, but that's in a solid. A deuteron can't accelerate in that solid. The voltage is there, but you can't get it going. So,
let us see once more. Most urgent question. Stand up. Okay. Bernd, stand. He has to be there. Microphone, please. It's coming. It's coming. It's coming.
I just want to add some not very well quantified results from other Russian papers along the lines of the speaker's notes. People have frequently measured both positive ions and electrons coming out of shredded cracks and shredded crystals, and they tend to be in comparable numbers. Furthermore, some of the Russian writers have claimed to observe X-rays with quantum energies up to 50 kilo-electron volts.
that's right. I agree with that. It's a literature which this group really has to read, because there are many examples of energetic particles coming from mechanically induced materials effects.
Okay. There's one last very important question. State your name.
Yes, check. Yeah, thank you. I have just a short
name
comment.
And
yes, my name is Ali Abu Taha, consultant from Reston, Virginia. My comment pertains to the dimensions used in your study. You said that you worked with a crack gap of 0.1 to 1 micron and a crack length of 100 angstroms.
No, 100 microns. Crack length.
You understand?
Crack length? The crack length that I plugged in there was between 500 and 1,000 microns.
I thought the number you put up said 100 angstroms.
No, 100 angstroms is the conduction path thickness around the crack. It's got finite thickness.
So the length that you used was several microns?
Yeah. The length of the crack to discharge the circuit was somewhere between a few hundred microns and 1,000 microns.
Okay, my fault. Thank you much.
Okay, let us decide that there's one last question. Please stand up, the one who really has to make. There's one. Okay.
Tanihata from Riken. That for the acceleration, it takes time. This is not acceleration of electron. And if you are talking about 50 picosecond or 500 picosecond of gap lifetime, I mean electricity lifetime, you can accelerate deuteron up to that energy. Okay, you may observe X-ray because you accelerate electron in there, but yes, not the deuteron.
Well, I agree. High energy positive ions are also found.
Okay, I think that was a very proper last remark. Thank you very much. We thank our speaker again. We have one last lecture before the very brief break. It's by Dr. Williams. Search for 0.8 MeV helium-3 nuclei emitted from palladium titanium exposed to high-pressure D2, Barwick, Price, and Williams from University of California at Berkeley.
Oh, it's working now. Okay, search for 0.8 MeV helium-3. Okay, can you hear me now? Okay. This work is stimulated actually not by the Fleischmann and Pons work, but more by the Scaramucci and collaborators' work. We felt that that was an easier experiment to try to replicate. Also, we thought this was an opportunity to look for helium-3. If the neutrons are truly created by fusion of two deuterons, then helium-3 should also be created. In order to detect the helium-3, we used a detector which has been used before for cosmic rays and also for alpha particles from radioactive sources and things like this. This is a plastic detector. For those of you not familiar with it, it works a little bit like an emulsion in that the initial damage caused by, for example, an alpha particle is invisible, but it is nevertheless there, and when you develop it chemically, you get an etch pit. And the etch pit has a nice conical shape, so you can tell that it's not a scratch or something else like that. And so this gives us a very clean indication of a track. There are background sources, of course. If you just take a raw piece of CR39 and etch it, one that's been stored for a while, you get radon tracks. In fact, CR39 in some modified forms is being used as a household radon detector. But what we do is we pre-etch for 8 hours. This removes all evidence of radon tracks. We have done experiments in the past that have shown that radon does not, in fact, get into the middle of the plastic. By the time it gets there, it's decayed. So we can etch for 8 hours, and that gets rid of all of that. We, of course, do have cosmic ray tracks in the middle. Many of these actually occur in the airplane flight when the plastic is delivered. And these, we do get real helium-3s and helium-4s inside the plastic. These would mimic our signal. However, the density of those tracks is very low. Main advantages of this detector are that it's very efficient. Basically, any alpha particle or helium-3 that impinges on the plastic will give you a track. It is site-specific. We can place a piece of hydride, palladium hydride, or titanium hydride right over the plastic, or just part of the plastic. And then we have another part of plastic that's not covered, and that's a background count. Let me show you a little bit of information about this plastic. I'm going to start with, we know sensitivity of this plastic for different particles. You know, if you actually get enough data, you can actually even separate things like helium-3 and helium-4. We're not trying to do that in this experiment, but you can see we have a clear separation between heliums and lighter particles. Although this can detect lighter particles, we're not claiming a detection, we're not claiming a limit on protons or tritons from fusion because the sensitivity depends on temperature. And you can see here, I should tell you what these axes are. I didn't tell you the axis on the first one, but maybe it's obvious. This is the residual range of the particle. This is how far the particle passes beyond the surface of the plastic. And this is the ratio of VG to VT. That's the ratio of the etching rates along the track and along the general surface. Here again is that ratio with one subtracted as before, plotted as a function of temperature. This, of course, is liquid nitrogen temperature, which was reached in the current experiments. You can see the sensitivity is less for the alpha particles. This was not done for protons, so we don't know for sure whether we can see them. In order to place, make sure that we had got deuterium into the titanium especially, which was a little more difficult than the palladium, we placed it inside an oven in a quartz tube, set the oven to 550 degrees centigrade and turned on the pump. After it was evacuated and reached 550 centigrade, we then emitted deuterium gas at a low pressure. By that I mean that we did not reach 1 atmosphere. It was less than 1 atmosphere, negative gauge pressure. This is partly because the apparatus was just not designed for pressure. But it's also proved to be sufficient to place enough deuterium in to get TiD2 and PDD.6. As I mentioned before, this is a schematic of how the metal hydride is placed against the plastic. And you can see we have an area over here for background counting. If the helium-3 goes the right way, it goes into the CR39. Also, of course, it must be within 1 micron of the surface. Otherwise, it will just stop in the palladium or titanium hydride. Then we place these within a cell. And here we do apply pressure of deuterium gas, after first pumping out, of course. And we can heat or cool this. In the experiments I'm talking about today, we only cooled. And heating just means bringing it up to room temperature again. We then cycled the temperature and pressure by first cooling the liquid nitrogen, leaving it for half an hour or so to make sure it was at liquid nitrogen temperature. Then we turned on the pump and took it out, let it warm up. This is similar to what Frascati and what was done at Frascati by Scaramucci collaborators. And then the second time, after pumping it out and warming it up, we emitted dry nitrogen to make sure we didn't get condensation on anything. Results we conclude from this, I've written 2 reactions up here which are commonly talked about. The results of this experiment only deal with the second reaction. If the first reaction occurs, we don't see that because it doesn't produce helium-3. Of course, it doesn't produce neutrons either. We did the temperature cycle, and we saw less than 3 tracks per square centimeter. That's the limit we can set, a 2 sigma limit, after subtracting the background on the part of the plastic that was not exposed to the metal. This corresponds to 5,000 helium-3s per gram for that experiment. And that's for each of the samples, less than 5,000 for this one, so 5,000 for that one. This is about 2 orders of magnitude or 3 orders of magnitude, depending on which experiment of Scaramucci and company you refer to, lower than what they got. We also did a couple of quick room temperature experiments looking for this first reaction, although if the second reaction had occurred, we'd probably be sensitive to that as well. We tried flexing some of the titanium hydride. I don't know if we flexed it enough to get the cracking that people have talked about, but we did flex it with a little clock motor turning around once every second. We didn't see anything. We can set a fairly low limit on that. I don't know how this relates exactly to the mechanism because, as I said, we didn't measure any cracking. Also, in samples left just to expose to the cosmic rays for 4 days at sea level, we can say that there are less than 40 fusions per cosmic ray stopping muon. Not per cosmic ray muon, but per muon that stops in that sample, which we can calculate. There are less than 40 fusions occurring per muon. Now, that's not a very good limit, but if we run this for a few months instead of a few days, we feel we can set a limit of less than 1 fusion per muon. I should point out also that with these experiments, we've done controls and we've done calibrations. For this one, for example, in order to calibrate this to make sure we could see alpha tracks with this particular plastic, because it does differ from batch to batch, we placed it in the same apparatus, but instead of putting in the palladium here, we put in a piece of glass which contains about 1 or 2% uranium. This gives you an alpha source which, like this alpha source, has a variety of depths from which the particles come. And we noticed that the efficiency was somewhat degraded by the temperature, that is, the efficiency for a person to be able to see the tracks. Presumably the tracks are still there. was degraded by about 20%, but I don't think that's significant. I think we can still be sure that we did not see any significant fusion. Thank you.
Yes, Brian Oliver from Rockwell International. What was the thickness of the palladium material you were using, and was it thin enough to have a significant fraction of the helium-3 recoil out into the plastic?
Only a very small fraction of the helium-3 actually goes into the plastic. No, it was about half a millimeter thick, and only a 1 micron surface layer is what we're actually sensitive to. But because our sensitivity is so high and our efficiency is so high, we can set a very good limit.
So can you back calculate then what the actual sensitivity would be for a bulk reaction in the palladium?
Yes, it's if the same rate occurs in the bulk, then we're setting a limit of less than 5,000 per gram for that run, which was about 8 hours.
Turkovich, University of Chicago. Your limit is 10 times lower than in the abstract. Is that correct? You have.
I don't.
You have 5 times 10 to the 4th there.
I don't know. Maybe there's a mistake in the abstract.
Well, you have first. You have 4 times 10 to the 4th per gram in the abstract.
I don't think that's right, but I'll certainly check into that.
Any other urgent question, comment? Let me just make sure that we understood it right. You have a sensitivity which is 100 times higher than Scaramucci, and you see no fusions at that level, correct?
Right.
Okay. Okay, there's one last, just behind.
Albert Chuan from Princeton University. I have a general comment about this type of fractal fusion. That is, since many people refer to the Russian paper, they should also look back to Asimovich's book, for example. And in the very early stage of the book, and he tried to give the reason of thermonuclear fusion by giving a curve that if you have monoenergetic ions and to produce fusion, it's many, many order of magnitude less than you would for thermonuclear. And unless that energy is is optimum at a certain energy. So essentially I'm saying this, that it's good to study this, to understand this, but to think that this is for fusion, it's really far-fetched.
Are there any pertinent questions or comments to this lecture? Important? No. In that instance, I would like to close this session. We have a very brief break. We'll reconvene on time at 10:30, since we cannot be late with considering various departures. After 10:30, we'll have a summary lectures by Dr. Schriefer and Hakeman. So please take your coffee rather rapidly.